Hey subscribers, I wanted to make a video response to one of Variablast's videos. What he's doing is he's trying to retessellate games like chess or checkers so that you can play the game with, say, a honeycomb pattern as a board rather than the traditional grid kind of pattern. But the problem is, based on the way the pieces move, it's kind of hard to translate one series of movements on one board to another. And I think I've figured out the solution to this problem, and I'm going to attempt to illustrate what I mean live to you on a piece of paper, and I hope this will work. Okay, so imagine this is a portion of a chessboard, and right here is your knight. I tried to draw a little horse. Looks more like a little devil Snoopy. Let's make it that. Anyways, suppose you wanted to move this chess piece, this knight right here. Now, you could say it's an L shape, or you could say it's moving a diagonal. Moving a diagonal and then to this side. But these two descriptions of the knight's movement depend on this grid layout, and we're trying to get rid of that. So we're going to have to re-describe this knight's movement in a new way. Okay, so here's one possible move the knight piece could make. Now here's a way of describing it that doesn't rely on the checkerboard pattern. Okay, so say we're starting out here. Now, it doesn't really matter which square you pick, so I'm going to take the top one. Now, the next move from here, I describe as being an even move. So, that means I label the sides like I have done here, 0, 1, 2, and 3, and then pick an even one other than 0, because 0 is the side that you crossed over. And, well, that leaves us only with 2. So, we move up onto crossover side 2 and move up onto here. And then we gotta pick an odd side. So here's 0, 1, 2, 3. We can either go here or we can go here. And there we go. We got the movement of a knight mapped out according to side indexes rather than up, down, left, right, because if you use a new tessellation, those definitions will be quite ambiguous. There's no genuine up, left, down, right in some cases, because you're just using different shapes. So if you use something that all shapes will have, which is a number of different sides, and you can label them, you can number them, you can use this system in any tessellation. And just to make things a little more clear with how this works, let's suppose you wanted to go in a different direction to start. And okay, so you're starting here and you pick a different route this time, and the reason I'm showing this to you is because it's supposed to show how this is all relative to the direction you're first going, or relative to the side you cross over. So you start over here, instead you go to the right. Now you do the same labeling thing again. You pick an even side, and then you'd pick another odd side, which could either be 1 or 3, and there you go. Notice how it's relative to the direction you came on. Now, if you wanted to extend this and to make another L from here, you'd probably go like this. 1, 2, 3. See, it's all supposed to be relative. But how would you apply this to, say, a hexagonal pattern? And I'm going to show you that right away. Alright, and here is the hexagonal tessellation. Now, suppose your knight was right here, and like before, we just pick any adjacent tile, like the top one here. And in order to make the next move, we have to, label the sides as I have done here, 0, 1, 2, 3, 4, and 5. But we have to pick an even side, which is either this one or that one, and I chose 2, just, to keep consistency. And then we move on to this tile, kind of like how it worked before. And this time, you know, we do use the same labeling. This is 0, 1, 2, 3, 4, and 5. And I chose 5 as the odd one. It has to be an odd one because, you know, that's how we described the previous movement. And in the end, we get here. So, in total, a knight's movement would be 1, 2, 3, like that. And there's one example. Now, I want to keep this short, so I won't go into too many different tessellations. I'm pretty sure you can figure it out. I mean, you can describe a similar process for crossing over vertices and going through diagonals, and it's really basically the same thing, same labeling, except with vertices there's two steps, because first you got to pick which vertice you cross over to, and then from there which polygon you move on to. So just to quickly go over that, I mean, I didn't plan on making these parts, but let's just quickly go over that. If you want to move a diagonal, first you pick a vertex, like say this one, and then from that vertex you pick another polygon. So in this case it'd be polygon, this would be, if this was polygon 0, this would be polygon 1, this would be polygon 2, this would be polygon 3, and when you were here this would be vertex, I don't know, well, I can't really decide which way to label it, but 0, 1, 2, 3, let's just go like that. And you can describe your the movement like that for diagonals, and it would work for it would work for other polygons too, because all polygons have vertices, and all vertices have adjacent polygons. And so there you go. And the best thing about this is that it eliminates the whole ambiguity of having, you know, the up, down, left, right that is only appropriate to describing grid patterns on game boards. And I've tried my best to eliminate that ambiguity by just, you know, saying the exact things that all polygons have, and using that as a way of describing the movement of chess pieces. And before I end this video, I'm just going to show, just for, you know, just for fun, all the different possible movements a knight could make using this kind of a checkerboard, this kind of, hexagonal honeycomb pattern. And I hope you found this video interesting. I'll see you later. Oh, I also wanted to add one more thing. The indexing doesn't have to go around counterclockwise, because if you do that, then if you have a polygon with an odd number of sides, then you're going to have a problem there, because there's going to be some asymmetricality there. So if you're having a shape with an odd number of sides, try a different method of indexing. Perhaps you can have negatives, like so here, let me just draw one here. It's kind of hard to describe visually. Alright. Pentagon. 0, -1, -2, 2, 1. And then you can have even or odd, like that. So, I mean, just to avoid confusion, say if you have a triangle. There you go. Or you can just, instead of having it as, you know, an offset, or even or odd, you can have like proportion. So do you use the opposite side? Do you use the side that is there 25% of the way around? That might not work as well, because I mean, you have to have something that will work with any tessellation. It has to have a, you know, an integral index, so you can have like a half on this side and half on another side. So I don't know, just experiment around. But you gotta use the basic elements of polygons if you're gonna have something that can work with any tessellation. And there you go. Hope you find that useful.